You believe you understand infinity. You are mistaken, not slightly mistaken, not missing a nuance, not lacking a detail. You are wrong about what infinity is. You have been wrong since the first moment you encountered the word, and every use you have made of it since has deepened the error. You drew the lazy figure 8 in the margin of your schoolwork and believed you had named something. You heard infinity and pictured the largest number, the number at the end of all counting, the final throne in a great hall of numbers stretching away beyond sight. There is no such throne. There is no such number. And believing there is has crippled your ability to understand the most fundamental truths about motion, change, and the architecture of the natural world. Let us begin with what seems obvious and then watch it collapse. You assume infinity is a number. Very well. Let us treat it as one and see what follows. Every number obeys the rules of arithmetic: addition, subtraction, multiplication, division. These rules are not suggestions. They are the laws by which quantity governs itself, as unyielding as the force that holds the moon in its orbit. And the most essential of these laws is this: every operation upon definite numbers must yield a single definite result. 5 and 3 make 8. Always 8. Not sometimes 7. Not occasionally 12. 8. This is what it means to be a number. Now apply this law to infinity. If infinity is a number, then infinity minus infinity must equal something definite, just as 5 minus 5 equals 0. But consider, take the collection of all whole numbers, 1, 2, 3, 4, onward, without end. This collection is infinite. Now take from it a second collection, all whole numbers, except the first 3. This second collection is also infinite. Both are infinite. Subtract one from the other, and what remains? 3. The first 3 numbers, left behind. But wait, you could have removed the first 7 instead, and the remainder would be 7. Or the first 1,000, and the remainder would be 1,000. Or every odd number, leaving infinitely many even ones behind. The same operation, infinity minus infinity, yields 3 or 7, or 1,000, or infinity itself, depending entirely on how you perform the subtraction. This is not merely a wrong answer, it is every answer simultaneously, and therefore arithmetic has not produced an error. Arithmetic has rejected the premise. The rules of quantity, which demand that each operation yield one result and one result only, cannot accommodate infinity among their citizens. Infinity does not break arithmetic by producing a wrong number. It breaks arithmetic by producing all numbers, which is the same as producing none. Whence it follows that infinity is not a number at all, not the largest number, not a special number, not a number of any kind. It does not sit at the end of counting, because counting has no end at which anything could sit. Imagine that great hall again, numbered thrones receding into the distance. 1, 2, 3, onward. You walk toward the far end, seeking the throne of infinity. You will walk forever, not because infinity is very far away, but because there is no far end. The hall does not terminate. There is no wall, no final seat, no throne waiting at the conclusion of the journey. Infinity was never waiting for you. There is no end to wait at. But here is the matter that most persons overlook. The symbol is partly to blame. That elegant figure 8 lying on its side, infinity, looks like a name for something. It has the appearance of a definite referent, just as the numeral 7 names a definite quantity. This is an illusion. The symbol infinity does not name a quantity. It names a tendency. the tendency of quantities to increase without bound. It is a shorthand for a process, not a label for a thing. Consider the word north. North is not a city. North is not a place on the map where you will eventually arrive if you walk long enough. North is a direction, a way of traveling, not a destination. You can walk north for 1,000 miles, and you will not be at north. You will merely have walked 1,000 miles northward, with north still stretching before you, as far as it ever was. Infinity is the north of numbers. It is not where they end. It is the direction in which they continue. Now, you might say, this is an interesting distinction, but a harmless one. What difference does it make whether we call infinity a number or a process? If it is merely a matter of language, why should anyone care? Because it is not a matter of language. It is a matter of everything. For 2,000 years, from the ancient Greeks to the age of the printing press and beyond, this single confusion prevented the most powerful minds on earth from answering the most basic questions about the physical world. Questions as simple as, how fast is this stone falling right now? Not on average, not over the next second, right now, at this precise instant. That question cannot be answered without infinity, and it cannot be answered by treating infinity as a number. The stakes of this misconception are not philosophical. They are written into the fall of every stone and the orbit of every planet. The ground has been cleared. The throne at the end of counting is empty, was always empty. And now the question presses, if infinity is not a number, what happens when mathematics needs it? Drop a stone from a tower. Watch it fall. It begins slowly, almost hesitant, as though uncertain of its purpose. Then it quickens. By the time it strikes the ground, it is moving with considerable force. Anyone who has had a stone fall upon their hand from a height will testify to this without hesitation. The stone's speed at the beginning of its fall is not its speed at the end. Simple question. What is its speed at one precise instant during the fall? Not the average speed over any interval, not over a second, not over a heartbeat, not over the smallest duration you can name. What is its exact velocity at one particular, indivisible moment? This question is not idle. It is the most important question in all of natural philosophy. The answer to this question, and the method by which the answer is obtained, unlocks the mathematics that governs every motion, every flow, every change in the physical world, from the trajectory of a cannonball to the orbit of Jupiter. And for 2,000 years, nobody could answer it. Here is why. To calculate speed, you divide distance by time. The stone falls a certain distance in a certain interval, and you divide one by the other. If the stone falls 16 feet in 1 second, its average speed over that second is 16 feet per second. Simple enough, but this is average speed. The speed smoothed out over the full second, as though the stone moved at a uniform rate throughout, which it manifestly did not. To get closer to the true speed at a single instant, you must shrink the interval. Measure the distance the stone falls in half a second and divide. The result is a better approximation. Measure in 1/10 of a second, 100th, 1,000th. Each gives a closer estimate of the true instantaneous speed. The pattern is clear. The smaller the interval, the more faithful the measurement. But to get the exact speed at a single instant, not an approximation, not a good enough estimate, but the true, precise velocity at one dimensionless point in time, it appears you must shrink the interval all the way to zero. You must divide zero distance by zero time, and that you cannot do. Division by zero is not merely forbidden by convention, like a rule of etiquette that might be relaxed in informal company. It is forbidden by the structure of mathematics itself. Admit division by zero and the entire edifice collapses. You can prove that 1 equals 2, that any number equals any other number, that the distinction between quantities dissolves into chaos. Division by zero is the one operation that arithmetic cannot survive. It is the abyss at the foundations. And here is the cruelty of it. Every interesting question about the natural world requires you to walk directly toward that abyss. What is the rate at which a fever rises, not on average over 6 hours, but at this very moment? What is the rate at which the tide turns, not approximately, not over the span of an hour, but at the precise instant the water ceases to rise and begins to fall? What is the exact curvature of a cannonball's arc at the apex of its flight? Each of these questions demands that you form a ratio of 2 quantities that are both shrinking towards zero. Each demands that you walk to the very edge of the precipice and somehow extract a meaningful answer without falling in. For millennia, the greatest mathematical minds turned back from this edge, and the error most make is supposing that the barrier was a lack of cleverness, that someone simply needed to be more ingenious, more persistent, more brilliant. This is precisely backwards. The barrier was not computational, it was conceptual. It was the false picture of infinity. So long as infinity was imagined as a destination, as a number you could, in principle, arrive at Borg, every attempt to work with vanishing quantities ended in paradox. The ancient Greeks perceived this with devastating clarity. Zeno posed his famous puzzles: the arrow that must be motionless at every instant, yet somehow moves across the room; the runner who must traverse half the remaining distance before traversing the whole, and therefore can never arrive. These are not riddles of philosophy. They are symptoms of a disease, the disease of treating the infinite and the infinitesimal as ordinary quantities that can be reached, held, and manipulated by the standard rules. The arrow paradox, the runner paradox, the impossibility of instantaneous speed, all are fruits of the same poisoned root. The assumption that infinity is a place rather than a process, a destination rather than a direction. And the consequence was not merely mathematical frustration. The consequence was blindness. The deepest truths about motion, change, and the continuous flow of nature remained sealed, not because they were inherently unknowable, but because the false picture of infinity stood between the human mind and the method needed to reveal them. The question that presses now is not, how do we avoid infinity? Avoidance is what created the barrier in the first place. The question is, how do we work with infinity without treating it as a number? How do we walk to the edge of the abyss and extract from it answers of perfect precision, without ever performing the forbidden division, without ever actually dividing by zero? The answer to this question changed everything, and it begins with a single transformative shift in thought. Let us attend carefully to what observation teaches. Return to the stone falling from the tower. You wish to know its exact speed at one particular instant, let us say, at precisely the moment it has been falling for 1 second. You cannot measure the speed at that instant directly, for a single instant has no duration, and speed requires both distance and time. But you can do something else. You can measure the average speed over intervals that surround that instant, and you can make those intervals smaller and smaller. Measure the distance the stone travels between 1 second and 2 seconds of falling. Divide by 1. You have an average speed over that 1 second interval. Now measure the distance between 1 second and 1.5 seconds. Divide by half a second. A closer approximation, between 1 second and 1/10 of a second. Divide by 1/10. Closer still. Now continue. 1/100th of a second, 1,000th, 10,000th. What happens? The averages do not scatter wildly. They do not jump and fluctuate without pattern. They converge. They settle with increasing precision toward a single definite value. Each smaller interval brings the average closer to this value. Each narrower measurement narrows the uncertainty. The averages approach a destination, not infinity, not chaos, but a specific, stable number. That number is the instantaneous velocity of the stone at the 1 second mark. And here is the essential revelation, the key that unlocks everything, the insight upon which the entire mathematics of change is built. You never need the interval to reach zero. You need only observe what happens as it approaches zero. This is the method of limits, and it is, without exaggeration, the most powerful intellectual instrument ever devised for understanding the natural world. The question is not, what is this ratio when the divisor equals zero? That question is malformed. It is like asking what colour is silence, or what weight has the number 7. The question makes a category error. It demands that a process produce an answer at a point where the process does not exist. Division by zero is not a difficult operation. It is a meaningless operation, and asking for its result is asking for the meaning of meaninglessness. The proper question, the question that transforms everything, is this: what value does this ratio approach as the divisor diminishes without limit? Not, what is the answer at zero? But, where is the answer heading as we approach zero? And the answer to this question is perfectly definite, perfectly stable, perfectly exact. Consider what this means. As the time interval shrinks towards zero, the ratio of distance to time does not careen off into chaos. It does not explode or collapse or oscillate wildly. It settles. It converges upon a single value with the same inevitability with which a stone released from your hand converges upon the earth. You never need the interval to reach zero, just as you never need the stone to have already arrived at the ground to know with certainty that it is heading there. The direction is plain. The tendency is unmistakable. The limit is determined. Whence it follows that the method of limits does not divide by zero. It never divides by zero. It watches what happens as the divisor shrinks towards zero and reads the answer from the tendency of the approach. The forbidden operation is never performed. The impossible question is never asked. Instead, a better question is posed, and this better question has a perfectly good answer. Now let us go deeper, for the principle has a subtlety that rewards close attention. When both the numerator and denominator of a fraction shrink towards zero simultaneously, common sense insists the fraction should become meaningless, or at least wildly unstable. Zero divided by zero sounds like mathematical anarchy, but common sense, in this instance, is wrong. Watch the actual behavior. Compute the ratio at each stage as both quantities shrink. At 1 second, the ratio has a certain value. At half a second, another, slightly different. At 1/10th, another. At 100th. At 1,000th. Plot these ratios, and you will find they do not scatter. They converge. The ratio of two vanishing quantities approaches a perfectly definite, perfectly stable value. This is the deepest counterintuitive truth of the method. The relationship between vanishing quantities possesses a stability that the quantities themselves do not. The parts are disappearing. The ratio holds firm. It is as though two travelers are walking toward each other from opposite ends of a bridge, each growing smaller as they approach the center. The travelers vanish, but the point at which they meet is precisely determined by their rates of approach. The meeting point is real, even though the travelers are shrinking. The ratio is real, even though the quantities are disappearing. This is what the method of fluxions accomplishes. It treats quantities not as fixed, frozen magnitudes, but as flowing things. Quantities in motion. Quantities that change. The very word fluxion denotes a rate of flow, and the method asks not what a quantity is at a frozen instant, but how it changes from one moment to the next, extracting from this continuous change a precise description of the quantity's behavior at every point along its course. The shift is total, from the static to the dynamic, from the snapshot to the motion, from the noun to the verb. And one further principle must be established before we proceed, for it addresses the question that will trouble the careful thinker. Do infinitely small quantities actually exist? Must we believe in them as real objects in order to use them? The answer is no. The infinitesimal is a device of reasoning, a scaffolding, erected to support the calculation and removed once the building stands on its own. One imagines a quantity shrinking without limit. One observes the tendency this shrinking produces. One names the tendency, calls it the limit, the fluxion, the instantaneous rate, and then one discards the imagined quantity because it was never needed as a real thing. Only its tendency was needed. Only the direction of its approach. The scaffolding is imaginary. The result is real. You can observe this principle in the simplest act of measurement. A craftsman smoothing a curved surface lays a straight edge against the wood. The shorter the edge, the more faithfully it follows the curve. An edge of 1 foot gives a rough approximation. An edge of 1 inch gives a finer one. An edge of 1/10 of an inch, finer still. The limit of this process, a straight edge of vanishing length, gives the true curvature at a single point. The craftsman does not need an infinitely short, straight edge. He needs only the principle that shorter edges converge upon the truth. Every act of careful measurement is, whether the measurer knows it or not, an application of the method of limits. The entire structure of this mathematics rests upon a single insight, that you do not need to arrive at the limit in order to know what the limit is. You need only observe the approach with sufficient care. The method works. This much is demonstrated, but the careful mind now asks, why does it work? What must be true about the nature of vanishing quantities and about the structure of reality itself for infinite processes to yield finite, exact results? Here is where most inquiries stop too soon. The method of limits has been demonstrated. The careful thinker has seen that the ratio of vanishing quantities can converge upon a definite value, that infinite processes can yield exact results, that the approach to zero is more powerful than the arrival at it. But a nagging discomfort remains, a feeling that something illicit is being performed, that dividing by quantities infinitely close to zero is a polite way of dividing by zero itself, dressed up in respectable language. This discomfort is understandable. It is also wrong. And it is wrong for a precise reason that must now be made explicit, for it is the hinge upon which the entire method turns. Zero and the infinitesimal are not the same thing. The error most make is collapsing this distinction, treating approaches zero as a genteel euphemism for equals zero. But the difference between these two conditions is not a difference of degree. It is a difference of kind. It is the difference between a candle that has been extinguished and a candle that burns still, however faintly. It is the difference between death And the last, faintest breath before death. It is the difference between silence and the softest sound still audible. A quantity that equals zero is nothing. It has no magnitude, no properties, no capacity to form ratios. It contributes nothing to any sum, and dividing by it produces not an answer, but a contradiction. Zero is the boundary between positive and negative, between existence and absence. It is the border of the realm of quantity, and beyond that border, quantity ceases to exist. But a quantity that approaches zero without reaching it is a different creature entirely. At every stage of its approach, it remains a legitimate, fully operational number. It can be doubled, halved, compared, and divided. It has a definite magnitude, small, yes, smaller than any quantity you care to name, but not zero. It inhabits arithmetic fully, obeys all its rules, forms all its ratios. It is a citizen in good standing of the Republic of Numbers, even as it walks toward the Republic's border. This distinction is not a quibble. It is the entire foundation. The method of limits operates entirely within the realm of legitimate numbers, quantities that are approaching zero but have not arrived there. At no stage does it require the quantity to actually be zero. At no stage is the forbidden operation of division by zero performed. The method is conducted wholly in the domain of the lawful, and its results are as legitimate as any arithmetic performed with ordinary numbers. But, and here the understanding deepens, not all approaches to zero are equal. Not all infinite processes converge upon a definite result. Consider. Take the numbers 1, -1, 1, -1, alternating without end. The partial sums of this sequence are 1, 0, 1, 0, endlessly oscillating. The process does not converge. It does not settle toward any value. It oscillates without rest, and no limit can be assigned to it. Or consider, take the numbers 1, 2, 4, 8, each double the last, and sum them. The partial sums grow without bound, 2, 6, 14, 30, onward, exploding toward infinity. This process does not converge either. It diverges. It is manifest, therefore, that the method of limits is powerful, not because it tames all infinities into submission, but because it provides a precise criterion for distinguishing the manageable from the unmanageable. Some infinite processes converge. They settle toward a definite value. Others diverge. They explode or oscillate. The method of limits tells you which kind you are dealing with, and for the convergent kind, it tells you exactly what value the process approaches. The question, does this process converge, is as essential as the question, to what does it converge? And the method answers both. Now let us see this distinction at work in nature, for nature is the tribunal before which all mathematical methods must justify themselves. Consider a loaf of bread. Divide it in half. Take one of the halves and divide that in half. Take the resulting quarter and halve it again. Continue without end. At each stage, the piece before you is smaller than the last, but it is never zero. It is always a real piece of bread with real weight and real substance. Now imagine summing all these pieces, 1/2 plus 1/4 plus 1/8 plus 1/16, onward without end. Common sense protests an infinite sum must yield an infinite result. But observe what happens. The partial sums are 1/2, then 3/4, then 7/8, then 15/16. Each is larger than the last, but each is also less than 1 ma, less than the whole loaf. The sums approach 1. They converge upon it with increasing precision at every step. The infinite process reconstitutes the finite whole. The infinite sum equals 1. not approximately, not for practical purposes, but with the same mathematical certainty that declares 2 and 3 to be 5. The infinite process has a finite, exact result, and that result is obtained without ever performing an infinite number of operations in practice. It is obtained by observing the tendency of the finite partial sums by the method of limits. This is the architecture that makes the calculus trustworthy. This is the foundation that separates legitimate use of the infinite from mystical hand-waving. The distinction between zero and the infinitesimal, between convergence and divergence, between the approach and the arrival, these are not subtleties for philosophers. They are the load-bearing walls of the most powerful mathematics the world has ever known. And with this distinction firmly in hand, we are prepared to confront the deepest paradox of all. Common sense now lodges its most forceful objection. You have shown, the careful viewer says, that the method of limits can extract definite values from infinite processes, that ratios of vanishing quantities can converge upon stable results. Very well, but you claim that this method yields the instantaneous rate of change, the speed of a stone at a single instant, the precise turning of a tide at a single moment. And this, common sense insists, is a contradiction. For how can something be changing at an instant? An instant has no duration. It is a dimensionless point in time, no more than a knife edge between the past and the future. Change requires time, a before and an after, a difference between one moment and the next. Within a single instant, there is no before and no after. There is only the instant itself, and within a durationless point, nothing can change. Is instantaneous change not, therefore, a contradiction in terms? It is not. But understanding why requires care. The objection is perfectly reasonable, and it has a long and distinguished history. The ancient Greek philosopher Zeno raised it with devastating force in his paradox of the arrow. An arrow in flight occupies a definite position at every instant. At each instant, it is here and not there. But if at every instant it is at one definite place, then at every instant it is motionless. It is at a position, just as a stone resting on a shelf is at a position. And if it is motionless at every instant, then it is motionless throughout its flight. Motion, says Zeno, is an illusion. The paradox is not foolish. It is, in fact, remarkably astute. And it remained unresolved for 2 millennia, precisely because it targets the genuine difficulty of defining what speed at an instant could possibly mean. Here is the resolution, and once seen, it cannot be unseen. Instantaneous rate of change does not describe what happens within an instant. Nothing happens within an instant. The instant is dimensionless. It has no interior, no room for events, no space for motion. On this point, common sense and Zeno are entirely correct. What the instantaneous rates of change describes is the limiting tendency of what happens in intervals surrounding that instant. It is the value that all sufficiently small measurements of average change agree upon. Think of it this way. Imagine you wish to know the prevailing sentiment of a district in a city. You cannot ask the district itself. A district is not a person. It has no voice. It holds no opinion. But you can ask its residents. Ask 10, and you get a rough picture. Ask 100, a closer one. Ask every resident in ever smaller neighbourhoods surrounding the centre of the district, and their answers converge. They settle upon a definite consensus. That consensus is real and meaningful, even though the district itself never said anything. The instantaneous rate of change is the consensus of the neighbourhood. It is not what happens at the instant, for nothing happens at the instant. It is what the surrounding intervals unanimously report about that instant. If you measure the stone's average speed over 1 second surrounding the target moment, you get one value. Over half a second, another, slightly different. Over a tenth, a hundredth, a thousandth, the values converge. They agree more and more precisely on a single number. That number is the instantaneous velocity. The instant does not contain the change. The instant is the point upon which the surrounding evidence converges. And here is why this matters far beyond the falling stone. Every process that changes direction, every tide that turns, every fever that breaks, every thrown stone that reaches the apex of its arc, passes through a moment where the rate of change is exactly zero. At that moment, the process is neither increasing nor decreasing. It is poised, balanced, suspended between what came before and what will follow. The moment of the turning tide, the moment of the highest point, the moment the fever breaks. These moments are invisible to average measurements. If you measure the tide's height every hour, you will find it higher at 1 hour and lower at the next, and you will know the tide turned somewhere in that interval. But you will not know when. Shrink the interval. Every half hour, every 10 minutes, every minute. As the interval narrows, the turning moment is located with increasing precision. The limit of this process of narrowing, the value the measurements converge upon, is the exact instant of the turn. The turning point is found by the method of limits. It cannot be found any other way. You experience such turning points constantly, though you seldom name them. The moment you cease walking forward and begin to turn around, there exists an instant where your forward velocity is precisely zero. The moment a pendulum reaches the summit of its swing, its speed is zero, poised between falling one way and falling the other. The moment the longest day of summer yields to the first faint shortening, the solstice, the hinge of the year, found not by observing a single day, but by observing the tendency of many days as the interval narrows. Each of these is an instantaneous rate of change passing through zero. Each is a limit. Each is found not by examining the instant itself, which contains nothing, but by examining the convergence of the surrounding intervals. And so, Zeno's arrow is answered at last. The arrow at a single instant does indeed occupy a single position. On this, Zeno was right. But its velocity at that instant is not determined by what happens at that position. It is determined by where the arrow was just before and where it will be just after. In the limit, as just before and just after, shrink toward the instant without ever reaching it. The arrow's velocity is a property of the neighborhood, not the point. The arrow is not motionless at each instant. It possesses, at each instant, a definite velocity. A velocity defined not by frozen stillness, but by converging tendency. The paradox rested on a false demand that the instant itself contain the motion. It does not. The motion is encoded in the pattern of the surrounding intervals. The method of limits reads the pattern. The paradox dissolves. We now possess the complete technical foundation. Infinity is not a number, but a process. The method of limits extracts definite, exact results from infinite processes by observing convergence rather than demanding arrival. The infinitesimal is distinct from zero. It is a quantity approaching the boundary, not a quantity that has crossed it. And instantaneous change is not a contradiction, but a precisely defined limiting concept. The consensus of vanishingly small intervals surrounding a point in time. What remains is to see what this method reveals when applied to the world. If a single principle governs the fall of a stone, the flow of a river, the orbit of a planet, and the turning of a tide, then what we have is not merely a technique of calculation. It is a vision of nature's unity, waiting to be assembled from the pieces we have gathered. There are two ways to know a changing thing, and the difference between them is not a difference of precision. It is a difference of kind. Consider a coachman who completes a journey of 40 miles in 4 hours. He reports his speed as 10 miles per hour. This is true as far as averages go. But you rode in that carriage. You felt what the number conceals. The horses plodded through mud for the first mile, barely moving. On the firm, straight road beyond the village, they broke into a gallop, 15, perhaps 18 miles per hour. At the river ford they stopped entirely, the wheels stuck in silt, the coachman cursing, the horses steaming. The final stretch was a weary crawl. The animals spent, the road rutted, 10 miles per hour. That is the fact. But is it the truth? The average speed contains every moment of the journey, the crawl, the gallop, the halt, and compresses them into a single number. And in that compression, something essential is lost. The texture, the character, the story, the moment the horses surged, the moment they faltered, the moment the journey nearly failed at the ford. The method of limits recovers what the average erases. By examining the journey in smaller and smaller intervals, not 4 hours but 1 hour, not 1 hour but 10 minutes, not 10 minutes but 1 minute, you reconstruct the speed at every moment. Each narrowing reveals detail the wider interval concealed. The 1 hour average misses the halt at the ford. The 10-minute average catches it, but misses the precise moment the horses broke into gallop. The 1 minute average catches even that, and the limit, the instantaneous speed, catches everything. Every surge, every hesitation, every transition from one pace to another. This is not merely a finer measurement. It is a different kind of knowledge altogether. The average tells you what happened in summary. The instantaneous rate tells you what is happening right now, and right now is the only moment at which anything can actually be changed. The navigator who knows only his average heading over the past week knows where he was. The navigator who knows his instantaneous heading knows where he is going. The first is history. The second is power. Whence it follows that every average in every domain is a concealment, not a falsehood. The coachman's 10 miles per hour is not a lie, but it is a compression that discards precisely the information that matters most, the turning points. And here we arrive at a principle of considerable importance. A turning point is the moment when a process reverses direction, when growth becomes decline, when acceleration becomes deceleration, when the tide ceases to rise and begins to fall. These moments are the hinges of the world's motion. They are where events pivot, where outcomes are decided, where the character of a process changes from one thing to its opposite, and turning points are invisible to averages. Consider a physician attending a patient with fever. At noon, the temperature is 101 degrees. At midnight, 103. The average rate of rise, 1 degree in 6 hours. This tells the physician the fever is worsening, but it tells him nothing about when the worsening accelerated, whether the fever paused during the afternoon, or, most critically, whether the fever has already begun to break. If the fever rose sharply from noon to 6 o'clock and has been falling since, the midnight reading of 103 might represent not a worsening, but a recovery already underway. The average hides this completely. Only the instantaneous rate of change, the rate at each moment, reveals the turning point. The turning point is where the instantaneous rate of change passes through zero. Before the turn, the rate is positive. The fever is rising. After the turn, the rate is negative. The fever is falling. At the turn itself, the rate is exactly zero. The fever is, for a single breath, doing neither. This moment is invisible to any measurement that averages across too wide an interval. It is visible only to the method of limits. The merchant who knows his annual profit knows an average. The merchant who knows his daily rate of change sees the life of his enterprise, the weeks of quiet growth, the single disastrous day when a shipment was lost, the moment in autumn when the market turned and what had been profitable became ruinous. The annual average says 10% growth. The instantaneous account says you were growing at 20% until the third week of October, when you began to lose ground, and you have not recovered since. These are not two versions of the same knowledge. They are different kinds of knowledge entirely. One is a skeleton, the other is the living body. But the depth does not stop there. The rate of change may itself be changing. Pour water from a jug into a basin. The water level in the basin rises, but not uniformly. At first, when the jug is full and tipped sharply, the flow is rapid. As the jug empties, the flow slows. The rate of rising is itself diminishing. There is a rate of change of the rate of change, a second-order rate, a curvature in the pattern of change. This is what the method of fluxions was born to describe. Not merely how fast a quantity is changing, but how fast the speed of change itself is changing. The first rate tells you the direction. The second rate tells you the curvature, whether the process is accelerating, decelerating, approaching a turning point, or pulling away from one. The falling stone demonstrates this with perfect clarity. Its speed increases as it falls. This is the first rate of change, the velocity. But the rate at which the speed increases is itself constant. The stone accelerates uniformly, gaining the same increment of speed with every passing moment. This constant acceleration, this unchanging rate of the rate of change, is the signature of gravitational attraction. It is the mathematical fingerprint of gravity itself, visible only to the mind that thinks in limits, invisible to the mind that thinks in averages. Notice then what happens when you shift from averages to instantaneous rates. You do not merely see the world in finer detail. You see a different world, a world of texture and turning points, of acceleration and curvature, of hidden structure lying beneath the smooth surface of every summary. The average is the outline. The instantaneous rate is the architecture. And between outline and architecture lies the entire distance between approximate understanding and genuine comprehension. From this moment forward, when you hear any average, any summary, any report of change compressed into a single number, train yourself to ask, what is the instantaneous story hidden within this summary? Where were the turning points? What texture has been erased? This is not a mathematical skill. It is a perceptual one. You believe the world is made of things, of stones and rivers and stars, of objects resting in their places, occasionally disturbed by forces that set them moving, until the forces subside and rest is restored. The stone sits on the table. The ship floats at anchor. The book lies on the shelf. These things are at rest, and rest, you assume, is their natural condition, the state to which they return when nothing acts upon them. This is precisely backwards. The world is not made of things that occasionally move. The world is made of motions that occasionally produce the illusion of things standing still. Consider the stone sitting on the table. It appears motionless. Nothing is happening to it. It simply is, inert and unchanging. But attend more carefully. The stone is being pulled downward by the same gravitational attraction that holds the moon in its orbit, a force that acts upon every particle of the stone, drawing it toward the center of the earth with relentless, ceaseless, continuous effort. If the table were removed, the stone would fall immediately. It would not pause, would not hesitate, would not need to be set in motion. The motion was always there, waiting. It was merely balanced, held in check by the table, which pushes upward with precisely the force that gravity pulls down. What you call rest is not the absence of force. It is the precise cancellation of opposing forces. It is not stillness. It is a balance of motions, a dynamic equilibrium maintained at every instant by the continuous action of competing influences. Disturb this balance by the slightest degree. Remove one leg of the table, tilt the surface, add a grain of sand to the stone, and the illusion of rest shatters instantly. Motion resumes because motion was always present. Only the balance concealed it, whence it follows that rest, properly understood, is not the absence of change. It is the limit of change as it approaches zero, the special case in which the instantaneous rate of change happens at this particular moment to equal precisely nothing. Stillness is not the opposite of motion. It is a species of motion, the species in which the rate is zero. And if rest is merely motion at zero rate, then the entire world, every stone, every river, every star, every object you perceive as fixed and stable, is embedded in a fabric of continuous change. The apparently static is merely the momentarily balanced. Now raise your eyes to the sky and consider the most spectacular demonstration of this principle that nature affords. The moon. It appears to hang motionless, a fixed, silvery disk suspended in the darkness. Night after night it returns to approximately the same position, drifting slowly among the stars, but never falling, never crashing to earth, never doing anything so dramatic as to betray the violence of what is actually happening. The moon is falling. At every instant, every single instant, the moon falls toward the earth. Gravitational attraction draws it downward with the same force that draws the stone from the tower. But at every instant, the moon's forward motion, its velocity along its orbit, carries it past the earth, so that the surface of the earth curves away beneath it just as fast as it falls toward it. The fall and the forward motion combine into a curve. That curve is the orbit. The moon does not defy gravity. The moon is the most elegant demonstration of gravity imaginable, a body in continuous free fall, whose fall is bent into a circle by its own forward speed. Its apparent stillness is an illusion of the most profound kind, the illusion produced by two motions in perfect, perpetual balance. Only the mind that thinks in instantaneous rates can see the fall hidden within the hovering. The average observer sees a disk hanging in the sky. The observer, equipped with the method of limits, sees a body plummeting toward the earth and continually missing it. Same moon, different understanding. And between those two understandings lies the entire science of celestial mechanics. This principle, that the world is made of motion and rest is merely balanced motion, carries an implication of extraordinary reach. If one method can describe both the falling stone and the orbiting moon, if the same mathematics of limits applies to the flow of a river, the curve of a cannonball's arc, the changing height of the tides, and the acceleration of a horse from walk to gallop, then we are not looking at a collection of separate phenomena governed by separate laws. We are looking at one phenomenon, continuous change, governed by one method, the method of limits. manifesting in 1,000 different costumes, but obeying a single set of principles beneath them all. There is not one mathematics for projectiles, and another for fluids, and another for celestial bodies. There is one mathematics, one method, one language of change, spoken by every moving thing in the universe. This uniformity cannot be accident. That a single principle, the approach to a limit, the observation of tendency, the extraction of exact results from infinite processes should illuminate every domain of natural change is a fact so remarkable that it demands explanation. Whether one attributes this uniformity to the wisdom of a divine architect or merely marvels at the architecture without naming its author, the uniformity itself is beyond dispute. The world is built for this mathematics. Or perhaps it is more accurate to say, this mathematics was built to read the world, to decode the language of continuous change that is written into every motion, every flow, every oscillation, every orbit. The stone obeys this mathematics. The tide obeys it. The moon obeys it. The cannonball and the pendulum and the river obey it. And the method by which we read their obedience is the method of limits, the method that works not by reaching the infinite, but by approaching it, not by grasping the answer, but by observing its tendency, not by arriving, but by disciplining the approach until the destination becomes as clear as if we had arrived. The vision is now complete. The scattered insights of the preceding chapters, infinity as process, the method of limits, the distinction between zero and the infinitesimal, the resolution of instantaneous change, the contrast between averages and instantaneous rates are not separate ideas. They are facets of a single understanding, that the world is a continuous flow of changing quantities, and that the mathematics of the infinite is the natural language of that flow. What remains is to ask what this understanding means, not merely for mathematics, but for the nature of knowledge itself. Here is the most paradoxical truth revealed by the mathematics of the infinite, and also the most consoling. A process that never terminates can yield results of perfect exactness. Let that settle. Let the strangeness of it register. You have been told, perhaps from childhood, that anything worth doing must be finished, that results come from completion, that answers are found at the end of inquiry, that understanding means arriving at a final, fixed, comprehensive truth. The mathematics of the infinite refutes this absolutely. It demonstrates with a rigour that no objection can overthrow, that the unfinished can be perfectly exact, that you can extract results of absolute precision from a process that has no last step. Consider the simplest possible example. Take the sum, 1/2 plus 1/4 plus 1/8 plus 1/16, continued without end. At each stage, the sum is definite and exact. After one term, the sum is 1/2. After 2, 3/4. After 3, 7/8. After 4, 15/16. At no stage whatsoever, does the sum equal 1. There is always a remainder, always a gap between the partial sum and the whole. And yet the sum approaches 1 with such irresistible, disciplined precision that 1 is declared its limit. Not approximately, not for practical purposes, not as a useful fiction, but with the same mathematical certainty that declares 2 and 3 to be 5. The sum of this infinite series is 1, in the fullest, most exact meaning of mathematical equality. The process never finishes. The result is perfect. This is not a trick. This is not a clever workaround for a deficiency. This is the fundamental nature of the infinite, rightly understood. Infinite processes, when they converge, produce results as exact as any finite calculation. and often more illuminating because they reveal structures that finite methods cannot reach. But here, the mind must be on its guard against a subtle error. The temptation is to imagine that the exactness depends on some hypothetical last step, that if only the process could be completed, the result would emerge in that final moment. This is the old misconception in disguise. Infinity as a destination, the last step as the last throne. There is no last step. There is no moment at which the infinite sum is finally performed. The exactness of the limit does not depend on completion. It depends on convergence, on the observable, demonstrable, verifiable fact that the partial sums approach a single value with ever-increasing precision, and that no amount of further addition will ever cause them to deviate from this approach. The limit is determined not by what happens at the end, for there is no end, but by the pattern of the approach. And the pattern is definite. It is as clear as the trajectory of a stone in flight, whose destination is plain to anyone who observes its arc long before it arrives. And now consider what this means beyond mathematics. If the most exact and powerful knowledge in all of natural philosophy, the calculus of change, the mathematics that governs every motion and every flow, is obtained not by finishing, but by approaching with ever greater refinement, then what does this say about the nature of understanding itself? We are accustomed to treating knowledge as a state of arrival. I understand gravity. I understand the motion of the planets, as though understanding were a room you walk into and then occupy, a destination, not a direction. But the method of limits suggests otherwise. It suggests that the deepest comprehension may be not a room, but a corridor, a process of continual refinement, each step more precise than the last, converging upon a truth that grows clearer at every stage, but is never contained in any single stage. The scholar who studies a question for a lifetime grows more knowledgeable with each passing year. Each year brings greater precision, greater depth, finer discrimination between the true and the almost true. At no year does the scholar declare the question finished, and yet is the scholar's understanding imprecise? Is it vague, approximate, close enough? It is not. At each stage it is exact within the tolerance that the current depth of inquiry permits. It is a partial sum that approaches the limit, and the limit, though never reached, is determined by the pattern of the approach. This is not a counsel of despair. It is the opposite. It is a liberation from the tyranny of finality, from the paralyzing demand that one must arrive before one can know. The method of limits teaches that precision does not require arrival, that exactness does not require finality, that the unfinished, rightly conducted, is as exact as the complete. You can observe this in the work of every master craftsman. The lens grinder who polishes a lens through successive passes, each finer than the last. Does he despair because perfect curvature can never be achieved? He does not, because each pass brings the lens measurably, demonstrably closer to the ideal. The limit of his process is a perfect lens. He will never reach it. But his lenses, at each stage, are exact to within the tolerance his method achieves, and those tolerances shrink with every refinement. His art is the method of limits made tangible, applied not to numbers, but to glass. Or consider the geometer who inscribes a polygon within a circle to approximate its circumference. A triangle gives a rough approximation, a square, somewhat better, a pentagon, better still. A polygon of 1,000 sides approximates the circumference so closely that the difference is imperceptible. A polygon of 1,000,000 sides, closer yet. At no stage is the polygon a circle. At no stage does its perimeter equal the circumference, but the limit of the process, the value the perimeters approach as the number of sides increases without bound, is the exact circumference of the circle. Known precisely, named exactly. The polygon never becomes the circle, but the circle is determined by the polygons that approach it. The unfinished can be perfectly precise. The incomplete can be exactly determined. And the demand for a final answer, for a truth you can hold like a coin in a purse, finished and fixed and fully possessed, may itself be a species of the same error that treated infinity as a number. Just as the mind that insists on reaching infinity is left with paradox, the mind that insists on arriving at final understanding may be frustrated, not because truth does not exist, but because truth is approached rather than occupied. The method of limits does not counsel uncertainty. It counsels disciplined approach, and it demonstrates with mathematical force that disciplined approach yields results as exact as any arrival could. And so we return to where we began. You came to this hour believing infinity was big, the biggest, the number at the end of all counting, the throne at the far end of the hall, the destination you would reach if only you could count long enough. You have been told over the course of these chapters that this belief is wrong, and not merely wrong in detail, but wrong in kind. Infinity is not a number. Bigness is a property of numbers, and infinity is not among them. But now, having traversed the method of limits, having watched vanishing quantities yield exact ratios, having seen instantaneous change defined with perfect rigor, having witnessed one method illuminate every domain of natural change from the falling stone to the orbiting moon, now you can see something the beginning of this journey could not yet show you. Infinity is not big. It is not a failure of the finite. It is not a deficiency, not a frustration, not a problem to be overcome. Infinity is a categorically different kind of concept. The misconception was never that infinity was too vast to comprehend. The misconception was that it was the same kind of thing as ordinary numbers, merely larger, that it lived in the same house, obeyed the same rules, answered to the same operations. It does not. It is not a bigger version of the familiar. It is something else entirely, a process, a direction, a tendency, a horizon. And recognizing this, truly recognizing it, not as a verbal formula, but as a shift in the architecture of one's thought, is itself a model for a deeper intellectual virtue. How many ideas have you carried throughout your life that were not wrong, precisely, but wrongly categorized? How many concepts have you treated as one kind of thing when they were, in fact, another kind entirely? And how much confusion has this miscategorization produced? The method by which infinity was tamed was not cleverness within the old framework. It was the recognition that the old framework did not apply, that what was needed was not a bigger number, but a new concept, a new method, a new way of thinking about what questions to ask and what answers to expect. This is the deepest lesson the infinite teaches, that the most important intellectual skill is not solving problems within a framework, but recognizing when the framework itself must be replaced. When a concept produces paradox after paradox, when every attempt to use it leads to contradiction, the error may not lie in your calculations. It may lie in your categories. You may not need a better answer. You may need a better question. Infinity demanded a better question. And the better question, what does this ratio approach, rather than what does this ratio equal at zero, unlocked the most powerful mathematics in the history of natural philosophy. not because it was a more ingenious answer to the old question, because it was a different question entirely. Now let us consider what this reveals about the world we inhabit. That the physical world should be continuous, that it should admit the method of limits at every point, in every domain, without exception, is not a mathematical convenience. It is a statement about the architecture of reality. Bodies do not teleport from one position to another. They pass through every intervening point. Temperatures do not leap from cold to hot. They traverse every intermediate degree. The planets do not skip portions of their orbits. They trace continuous curves through space, every point determined, every moment accounted for. The world is built for this mathematics. Every motion is continuous, every change is smooth, every process admits the method of approach. And the method that reads these motions, the method of limits, of fluxions, of infinitesimal analysis, is not imposed upon the world by human ingenuity. It is read from the world. It is the language the world was already speaking before any human ear learned to hear it. The stone falls from the tower. At every instant it possesses a definite velocity, a velocity we now know how to define, how to calculate, how to understand. The stone does not know the method of limits. The stone has never heard of fluxions or infinitesimals or convergent processes. But the stone obeys this mathematics with a precision that no instrument can fault. The continuous curve of its acceleration, uniform, unvarying, governed by the constant pull of gravity, is a limit calculated by nature itself, written into the fabric of the fall before any human mind conceived of calculating it. We are not inventing the mathematics of the infinite. We are recovering it, reading what was always written in the motion of the world, decoding a language that was spoken before we arrived and will continue to be spoken long after we depart. And this is why the method of limits, properly understood, inspires not frustration, but wonder. It might seem that a method which never arrives, which works by approaching without reaching, by observing without grasping, by extracting precision from the unfinished, should leave us unsatisfied. We want answers, and the method refuses to give us the last answer. We want to cross the ocean, and the method tells us to study the tides from the shore. But consider what it gives us in return. From the shore, we read the tides. We chart the currents. We compute the depth. We discover laws written in the water's motion, laws as certain and as beautiful as any treasure the ocean floor could yield. We predict the movements of celestial bodies decades before they occur. We calculate the curve of every projectile, the flow of every river, the oscillation of every pendulum. We know the precise instant at which the tide will turn, the exact moment the solstice arrives, the speed of a falling stone at any point in its descent. All of this, all of it, obtained from the shore by the method of disciplined approach, without ever crossing the infinite ocean that lies before us. The ocean's infinity does not defeat us. It defines the conditions under which our knowledge operates. We do not conquer the infinite. We learn to work at its edge, and the precision we extract from that edge is not second best, not approximate, not as good as we can get. It is exact. It is perfect. It is, by the rigorous demonstration of the method itself, as certain as any knowledge that could be obtained by any means. This is the gift of the mathematics of the infinite, not mastery over the boundless, but precision at the boundary. Not the final answer, but the disciplined approach that yields exact results at every stage, converging always toward truth, never arriving, never needing to arrive. And so, let us end where all honest inquiry must end, not with the satisfaction of completion, but with the opening of a door onto something vaster. The great ocean of truth stretches before us, inexhaustible and deep. We stand upon the shore, and from this shore we have learned to read the tides, to decode the mathematics written into every motion, every change, every continuous flow of the natural world. The ocean does not shrink, the shore does not advance, but our instruments grow finer, our methods more precise, our readings more exact. And with each refinement, the laws we discover are not approximations, but truths, as certain and as elegant as the architecture of the cosmos itself. You entered this hour believing infinity was a number, the biggest number, the last number, a destination you might reach if you counted long enough. You leave understanding that infinity is not a number at all, but a horizon, the boundary against which all finite knowledge is measured, the backdrop against which every answer stands in relief. The misconception was never that infinity was too large to comprehend. The misconception was that it was the same kind of thing as the quantities we ordinarily handle. It is not. And the moment we recognize this, the moment we stop trying to force the infinite into the mold of the finite, it yielded its secrets, not grudgingly, not partially, but with an exactness and an elegance that speaks of deeper architecture, of a world designed to be read by precisely this method. The stone falls, the tide turns, the moon orbits, the pendulum swings, and in each of these, in every motion, every change, every continuous flow, the mathematics of the infinite is at work, silent and exact, computing limits that no human mind conceived of and no human hand set in motion. We did not invent this mathematics. We recovered it. We found it written in the fall of the stone and the arc of the moon, and we named what was always there. And the ocean of truth remains before us, vast, unexhausted, infinite in the only way that infinity can honestly be described, not as a size, but as a direction, not as a place to arrive, but as a horizon that retreats as we advance, sharpening everything we see by providing the contrast against which all knowledge becomes clear. Infinity is not the answer to any question. It is the horizon against which all answers become clear.